Here's an introduction to parametric. There's various variations on how you say this. Parametric equations. I would prefer to say it's about parametrized curves. It's really about a particular algebraic way to talk about geometry. And there's an example that I like to start with, which we actually know already. We're going to look at the unit circle. And one equation for the circle is what we could call an implicit equation. X squared plus y squared equals 1. That comes from Pythagoras. It says that if I'm xy and I want to test if I'm really on the circle, what I do is I calculate x squared plus y squared, which is the hypotenuse of this right triangle. That would be the radius of that circle. If that's equal to 1, then I'm on the circle. One of the things about implicit equations, just while I'm on the subject, is that to really understand them, you actually have to think about what happens if I took an xy, like 4 minus 2, that wasn't on the circle. Sometimes you get this idea that it's only about testing these points. Well, you can test these points, and these are the points that give you the answer yes. You can plug these into the left-hand side. You just won't get that it's equal to 1. It will be one of those things where the equation turns out to be false. And so you test that, and you say, oh, that's not on the circle. So that's an implicit description. It's great if you give me a point and I want to test whether it's on the circle, but it's not great for generating points on the circle. Okay, well, there is a way to generate points on the circle. We could just solve that for y. Okay, sorry, well, actually, let's erase everything so I get some room. We could just solve it for y. Y equals plus or minus the square root of 1 minus x squared is the solve of that. And that's how you graph it on the calculator, for example. But there's a lot that's ugly about that. The square root is kind of a nasty function in a lot of ways. The plus or minus, you're breaking it artificially into 2 halves. There's not really any great reason we should have to break it into 2 halves. The other reason it's not so great is, for example, if I give you a lot of like uniformly spaced x values. Well, first of all, if I accidentally pick an x that's not between minus 1 and 1, I'm not going to get anything. So I have to know that in advance to make this work. And if I pick some uniformly spaced x values, like 0, 1 minus 1, or minus 1, minus 1 half, 0, 1 half, 1, I'm going to get some points on the circle, but they're not uniformly spaced. If you look carefully at how these guys go, the spacing is not going to be the same. And so there's some real disadvantages of this. Well, we actually already know a much nicer way to generate points on the unit circle, and that's to pick any t value, any real number t, and then just set x equal cosine t and y equals sine t. Well, what does that do? That has a lot of advantages. Actually, let's put it back down here. Because what is the t? The meaning of t here is just the theta. And we're definitely going to do this in radians, because whenever we do circular trig, things that are really focused on the circle and not so much about the triangles, it's almost always better to do it in radians. That says that I'm going to, if I pick t equals 0, I start out here. At t equals pi over 2, I'm up here. Where am I halfway in between? Oh, I'm actually geometrically halfway in between. If I pick t equals pi, I'm twice as far around as pi. What I'm doing, what I want to think about here, the reason I call it t, is that I want to think of t as a time variable. I feel like my focus is not very good. Sorry, I'm just going to do a little auto-focusing here. That seems maybe better, hopefully. I'm going to think of t as time, and I'm going to think of this as describing the path of a particle or something. People usually call it a particle, but I think it's more fun if it's a bug just crawling on my whiteboard here. And so this could be the path, and I'm going to actually put in an arrow here for the path of that bug. And this description not only traces out the circle, put in a couple more points here, but gives me a very explicit description of the motion of the bug. Okay, so there's lots of good things about this description, that if it's the path of the bug, then this is including exactly when it was everywhere. It includes an idea of motion. It's possible to calculate things like the velocity of the bug, which you do in calculus. And at least it's possible to say which direction it was going, because you just go from lower to higher values of t as you go around. And back to what I started with implicit versus, now this is explicit. This is a great way to sort of uniformly create a bunch of points on the circle very easily, as long as you know these magic functions, of course. But, of course, that's something we did a lot of last semester with cosine and sine. So we're going to look at a lot of these kinds of situations where instead of having some implicit equation, some yes or no test for an x and y that you give me, we're going to have what's called a pair of parametric equations. For example, like x equals t cubed, y equals t squared. And the idea is that we plug in various values of t, create points x comma y based on that t, and draw the curve that way. And so that's going to be the path of some particle. And this one, it turns out, has a kind of funky shape with a little super sharp corner down here. It's going like this. We'll maybe do this one explicitly soon enough. And one thing that we do want to think about for parametric equations is the time might not be all real numbers. We might want to explicitly say the bug started when t was -1 and then it ended at time t equals +1. Then we would get a restriction of this curve. This tells us that, for example, x is also, because that's t cubed, that's never going to be outside the region -1 to 1. If I cube a number that's less than 1 or bigger than -1, its cube is not going to be outside this region either. So if you believe me on this curve, which I don't think I want to take time to do explicitly right now, I want to make it too long, then it would just be this portion. And so that's very useful if you want just kind of an artificially truncated piece of a curve. It's a little harder to do with an implicit description. It's a very natural thing to do when you think of it as the motion of a particle, because there might be a starting time and a stopping time. Just one other thing about the times and everything. The extra information. This is something that not everybody emphasizes, but I like to emphasize. The point here is often not just to have a different way of drawing the same old curve like a unit circle. We often care about the extra info. So that's the t values. Like when I put on, like this is t equals pi over 2, I might well care about that explicitly. And the arrow of motion. And I always require, when people graph parametric curves for me, that we put on at least a few t values and the arrow to give an idea of the motion. We care about the extra info. So one way to say it is, I probably should have gotten this off the web, but here's the United States. Okay. Yeah. And I'm going to draw something. I'm going to draw a curve. This could be my family trip starting in St. Louis, Missouri, and going off to the West Coast, going this way, going the southern route first and then the northern route, in 2011, last year. Now, I didn't make a family trip like that, but it could be. It could have been. Okay. And it could have taken all of 6 days. Or it could be Lewis and Clark's route in, I'm going to get the number wrong, something like 1803. And it could have gone this way, which I think is more accurate, although it's certainly not precise at all. And it could have taken, over a year. And if I just give you the curve and I don't give you any t values or any arrows, you can't tell the difference between those two drastically different things. And that's one thing I want you to remember in terms of the extra info that we get with a parametrized description. We get those t values, like this is t equals 1803, this is t equals 1804, and then we're back here 2 years later. I'd have to look up exactly how long they took, but they took a long time. That Lewis and Clark information that you would get on a really good map of their trip is parametrized information. It's not just the set of points where they set their feet. It's when and in what direction they were going. So that's something I like to emphasize.